When a light turns on, what is electricity actually doing inside the wire? It's not magic, it's tiny particles moving in a very specific way. In this segment, we'll break down how electrons flow only when there's a complete circuit, and what voltage really means as a push behind it. And we'll connect that to how power plants use generators and moving magnets. Ready to see it clearly? Start small. Everything is made of atoms. Inside, atoms are positively charged protons and negatively charged electrons, and that charge difference matters for electricity. Electrons aren't all equally stuck. Some sit in outer shells, and an outside force can free them from their orbit, making them available to move. Once electrons are free, electricity is basically their movement. Those negatively charged particles hop from one atom to another through a material. For that movement to happen easily, you need a conductor. A metal wire, like copper, lets electrons travel through it without getting stuck immediately. But electrons can't just wander anywhere. They must have a continuous, unbroken path, a circuit, so the flow can keep going instead of stopping. That's why a switch matters. When the switch is open, the circuit is broken, so electrons can't complete the path and devices stay off. Close the switch and the circuit becomes complete. Now electrons have a full loop through the wire and the device can be powered. Even with a closed circuit, electrons need a push. Voltage is like pressure, analogy, the force that drives electrons through the circuit. So far, we've seen the basics. Atoms have electrons, some become free and they flow through a conductor only when a circuit is complete and the switch is closed. Voltage acts like pressure pushing that flow along, but here's where it gets interesting. Real circuits also have resistance that controls the flow, and we still need to explain where the push comes from in the first place, like at power plants. That's the next piece. Resistance is the restriction of electron flow. It's like narrowing a hallway. Electrons still move, but it's harder, and that changes what the circuit does. In many appliances, resistance is useful. By resisting the electron flow, parts can generate heat or light, like a heating element or a glowing bulb. Now zoom out. Electricity is a secondary energy source converted from primary sources like coal, nuclear, wind, or solar power. At power plants, electricity is typically generated by spinning generators. The generator creates a magnetic field that forces electrons to move through the circuit. Another simple way to say it, moving magnets can push electrons. That motion helps create the conditions for electricity to flow in wires. To power a device, you need three basics: a conductor like a wire, a complete circuit, and enough voltage to push electrons through. One important caveat, we're keeping this at a simple conceptual level. We're not detailing deeper generator physics or giving numbers for voltage or resistance. Electricity is the flow of electrons through a conductor in a completed circuit. A closed switch completes the path, voltage provides the push, and resistance shapes how that flow turns into heat or light. We also kept it intentionally simple. No numbers and no deep dive into how generators' magnetic field works beyond it forces electrons to move. But now when you flip a switch, you know what's happening inside the wire. Pretty cool, right? Thanks for watching. If this made you curious, leave a question or topic you want explained next in the comments. I'm turning everyday questions into short explainers, so subscribe if you want to see more.